On September 1st of last year, a team of 16 scientists made a groundbreaking discovery that sent shockwaves through the scientific community. They published a paper detailing their findings, which challenged our fundamental understanding of the universe. Using the powerful James Webb Space Telescope, these researchers observed distant galaxies and unearthed something truly unexpected. Until this discovery, the prevailing notion in astrophysics was that the universe underwent a period of rapid expansion followed by a cooling phase. This cooling phase eventually led to the formation of the first stars and galaxies during what scientists refer to as the Dark Ages. However, the galaxies observed by the team appeared remarkably developed, resembling our own Milky Way and indicating a level of maturity far beyond what was anticipated. This revelation suggested that these ancient galaxies must have existed long before our own. This finding carries profound implications for our understanding of cosmic history. It challenges the traditional narrative of the universe's origins, particularly the widely accepted concept of the Big Bang as the definitive starting point. While the Big Bang theory posits a singular event that marked the beginning of our universe, the discovery of these ancient galaxies suggests a more complex timeline. Prior to the early 19th century, the prevailing view among scientists was that the universe was static and unchanging, with no expansion or contraction occurring. This belief was upended by the observations of astronomer Vesto Slipher, who noticed certain nebulas exhibiting rapid motion away from us, attributed to the motion of our own galaxy. Further observations, particularly from the Lick Observatory in Arizona, contradicted this explanation. The pivotal figure in unraveling this mystery was Edwin Hubble, who demonstrated a clear correlation: the farther a nebula was from us, the faster it appeared to be moving away. This empirical evidence aligned with the predictions of Albert Einstein's theory of general relativity, which suggested that spacetime could expand or contract. By tracing the universe's expansion backward through time using the equations of general relativity, scientists arrived at the concept of a singularity, a point of infinite density and temperature from which all matter and energy originated. This singularity is often associated with the event known as the Big Bang. However, this raises profound questions about what existed before the Big Bang, if anything. Was there truly nothing, no space, no time, or are there aspects of cosmic history that remain beyond our current understanding? To visualize this concept, consider the analogy of the surface of a balloon. Imagine our universe as the surface of the balloon, expanding from a smaller size to its current dimensions. As the balloon expands, objects marked on its surface move farther apart, illustrating the concept of cosmic expansion. In this framework, the scale factor serves as a measure of the universe's size, analogous to the ruler used to measure the balloon's dimensions. At present, our universe has a certain scale factor, but in the past, it was smaller. As the universe expands, galaxies and other cosmic structures move away from each other, driven by the stretching of spacetime itself. In the future, the scale factor of the universe will continue to increase, reflecting the ongoing expansion of the cosmos. This perspective offers a glimpse into the vastness and complexity of cosmic history, inviting further exploration and inquiry into the mysteries of the universe's origins. As you slowly let the air out of the balloon, everything on its surface begins to draw closer together. Eventually, if you were to completely deflate the balloon, you'd be left with a tiny flat piece of rubber. This is akin to the concept of the singularity, a point in the universe's history when everything was incredibly close together, intensely hot, and extraordinarily dense. If we extrapolate the equations of physics backward in time, we arrive at a moment roughly 14 billion years ago when the temperature and density of the universe became infinite. However, just as we start to grapple with this notion, it becomes evident that the situation may not be as straightforward as it seems. Current evidence suggests that we shouldn't necessarily apply Einstein's equations all the way back to a singularity. Observations hint at a critical moment just before 10 to the power of -32 seconds after the Big Bang, during which the universe underwent a rapid expansion known as cosmic inflation. This period of inflation provides crucial insights into the universe's expansion on a grand scale, explaining why the universe appears so uniform and shedding light on the formation of galaxies. Yet even with the concept of inflation, the singularity remains a challenging concept. Its extreme density and temperature bring quantum forces into play, complicating our understanding. General relativity alone may not suffice to fully comprehend the phenomenon of the singularity. This early period of rapid expansion helps resolve some of the puzzles within the Big Bang theory, but it also prompts a re-evaluation of our understanding of cosmic inflation and the universe's origins. The peculiar nature of the singularity suggests that it might not represent the entire picture. Mathematical singularities often indicate gaps or limitations in a theory. In the case of the singularity, the clash between general relativity and quantum mechanics highlights the need for a more comprehensive understanding. Scientifically, we're still exploring the idea of whether there was truly a beginning to space and time. Sir Roger Penrose has proposed a new framework suggesting that events crucial to the formation of the universe, including the creation of galaxies and stars, may have occurred before the Big Bang itself. This challenges our conventional understanding and opens up new avenues of exploration. In this broader context, the universe's ultimate fate remains a subject of speculation. As we fast forward through time to infinity, envisioning a universe dominated by photons as black holes evaporate away, we confront the timeless nature of these particles. Photons, following null geodesics, move along paths where time and space essentially cease to exist for them. They are, in a sense, instantaneous, traversing the fabric of spacetime without experiencing the passage of time. Imagine turning on a flashlight for a brief moment and then switching it off. The instant the light shoots out from the flashlight marks event A, while the moment it reaches a certain point away from the flashlight represents event B. The space-time separation between these two events is calculated using the equation \ds_2 equals 0 \. This means that the photon emitted from the flashlight moves from event A to event B simultaneously, traversing through both time and space in a way that cancels out any net change in the space-time interval. This unique behavior of photons, where they lack a rest frame and do not possess a personal clock, aligns with a fundamental principle in physics, the constancy of the speed of light. No matter where you are or how you're moving, light always moves at a consistent speed. If photons had a stationary reference point, it would seem as though light isn't moving from their perspective. This fact challenges our understanding of the speed of light and highlights the peculiar nature of photons. The equations governing light, known as Maxwell's equations, possess an intriguing property: they are conformally invariant. This means that the equations remain unchanged regardless of whether you scale up or down the system. In essence, the vastness of the universe or the minuscule scale of quantum particles all appear the same when described by these equations. By applying this conformal picture to the concept of the Big Bang, we can imagine a scenario where the universe's initial state extends beyond the traditional notion of the Big Bang singularity. This mathematical approach allows us to characterize the universe's beginning in a way that extends back indefinitely. Einstein's theory of relativity provides crucial insights into understanding when the universe began. According to Einstein, energy and mass are interrelated, and this relationship is further elucidated by Max Planck's equation linking energy and frequency. This interconnectedness between mass and frequency underscores the role of mass in defining the passage of time. As we contemplate the remote future of the universe, we envision a scenario where the universe becomes essentially empty, populated only by photons. In this distant future, the universe's state may resemble that of a new Big Bang phase, suggesting a cyclic nature to cosmic evolution. This concept, known as conformal cyclic cosmology, challenges conventional ideas about the universe's beginning and end. It suggests a continuous cycle of expansion and contraction, where each cycle mirrors the previous one. This cyclic model emphasizes the significance of the Hubble parameter, which measures the rate of the universe's expansion. As the universe expands and contracts in a continuous cycle driven by the interplay of dark energy, it embodies a timeless and interconnected reality where past, present, and future intertwine. In our day-to-day lives, time flows continuously, shaping our experiences as a sequence of moments or snapshots. Each moment unfolds, leading to the next in a never-ending cascade of events. If we were to envision all these moments lined up, every earthly occurrence and every event in the vast expanse of the universe, it would capture the entirety of cosmic history. From the explosive birth of the Big Bang to the formation of stars in the Milky Way, from the emergence of life on Earth billions of years ago to significant events happening as we speak, they all coalesce into our sense of now. But Einstein's theories of relativity introduce a fascinating twist to this seemingly straightforward concept of now. According to special relativity, an entity's perception of time can differ depending on its motion. This means that individuals in motion will experience time differently and may slice through the fabric of spacetime at varying angles, shaping their unique now slices.